have not taken the exam yet, and they're not going to get this one because they're going to see all, so we'll make it fair. So those who haven't taken it yet will get a different one. It'll be the same type of stuff. It'll be painful, and make sure I get yours back so I can get your score in. All right, except that pretty much. Now let's go to your Mr. Gregory, and we'll get that in. Okay, because it's a nice round number that I remember. Okay, now let's go over it real quick, real quick, and we're going to go through this thing in about 8 minutes. You're going to be like, that's all there was to it? Well, yeah. Now you got to remember, I've graded 184 of these now, so I've got it down. I've got it kind of memorized. All right. So here's the deal. On the first one, the average thing is, well, theta, you had to find, they gave you S, which was 2.85 meters, which equals R times theta, and they gave you R was equal to 2.5 meters. Some of you used 2, and that's what kind of caused you a little bit of heartache. All right, you had to use 2 in the second part when you're getting this tangential velocity. All right, and so 2.85 divided by 2.5 gave you 1.14 radians. All right, and then theta over t equals your average thing. And so you divide that whole thing by 2.15. Ta-da, and you got about 0.53 radians. A lot of you got per second. A lot of you got 0.66 because you divided by 2. Okay? All right, and then the second part, the average tangential velocity then would be the radians times the radius of the buoy from the center. Okay? That's its average. All right? Now then, number two. I didn't want it to be as hard as it seemed. It was AC equals 4 Gs, basically, which equals 39.2 meters per second squared. All right, because G is 9.8. All right, and that equals V squared over R. So R just equals V squared over 39.2, which came out to be about 91 meters, right around there. A lot of you nailed that one. Some of you got a little confused. Some of you just divided by 4, which was a problem. But you didn't lose all your points if you just divided by 4. I mean, I knew what you were doing, but okay. All right, the next problem. The next problem, I've thought about this problem for a while when I put it on there, and I thought, oh, I should probably take that wet towel off there because you don't use it at all. You don't need it, okay? And some people were getting confused by that because you kept putting your M in there. But basically, it said that this one, AC, was equal to 10 Gs, which is equal to 98. A lot of folks, meters per second squared. A lot of folks got 980. That's test anxiety coming in. Or you just think, okay, so that's the tangential, that's what it needed to get up to. And AC does not equal R alpha. That's AT. Some of you had that one down. I said, no. That's AT. Okay? So, but you were right. We do have to, but you do need to get AC. We were looking for alpha. And I finally figured out, now that you guys have been a good guinea pig, I finally figured out how to teach this section. You got to teach you all the language, more so than all the math stuff. What do we mean by angular acceleration? What do we mean by angular velocity? Alpha is angular acceleration, and it's the change in angular speed, which is omega. Okay, AC actually equals R times omega squared. Well, so you got 98 divided by 0.35 square root equals omega. All right, and then alpha just equals omega over t. Okay? Which equals 6.69 So that's which was about 6.7 radians per second, something like that, squared. All right, then the next one was just an algebra problem, really, and it caused some people heartache, I think, because of that screwy thing where you had to get the period of, what was it, 28 or 27 days? It's 28 days, 27 days? What is it, 27? Yada, yada, yada. 27 days, right. That's a moon. 27 days, about 4 weeks, almost. All right, now, you had to get that into seconds, but really, V equals 2 pi r, which was given, divided by t. And you had to get t in seconds. And we also know this, that V squared over r equals the acceleration, which equals gme over r squared. So what I wanted was a formula for me. And you get v squared r over g is what a lot of you got. Some of you actually put all this stuff in there. You put 2 pi r. This is what I was really wanting. But if you can't give me this, that was fine, because a lot of you put this, and then you said this. It was that, and that was okay. Times r over g, which is kind of ugly. We could mess with that a little bit more if we wanted to, but you basically wind up with Kepler's equation, which is a funny looking thing, 4 pi squared r cubed over t squared g equals the mass of the Earth. That's kind of the simple, that's what I was after. Nobody got that. So I just said, well, I'm being a little ambitious, so I took this guy. I said, this is good. We'll take that. I'll take it. Okay. All right. So that was the first one. So I was actually looking for a formula. So a few of you, I took 2 off. You did a lot of hard work. I said, I still took 2 away because you got a formula. And then if you showed your calculations, you got the next part. Most people got the second part. All right, 5. 5 was killer. 5 was a killer. And we're gonna do energy until you're blue in the face. I'm going to beat it into you. All right, now, all right. Let's get all the preliminaries out of the way, and that's probably another thing that I should teach you better is how to set up a problem. You got to read the whole thing and look what you have and see what you got to do. All right, so we started off, and nobody in here did, but it's a problem. Well, actually, we had one person or a few people, and it was notoriously, and I don't mean this in any bad way, any non-PC way. You've got to be real careful when you design a test, especially in all these science classes, because we have all these people where English isn't their primary language. And so a lot of people got confused when I had that V of the ball. They thought that was the velocity of something. They thought that I was trying to be helpful, and I was actually causing problems because they were going, oh, that's the velocity of it. I'll stick it in there. No, 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 no. It's volume. That's the volume of the ball. Okay? All right. So what we had to do was, and we were given the radius of the ball is 0.108, and we were given this was annoying. I should have just given you the mass of the ball. I didn't think under test conditions. This would have been fine for a homework problem, but under test conditions, I should probably rethink that. But everybody came through pretty good on that. Is equal to kilograms meters cubed. Now notice this is density. That's not how much mass it has, but we can get that from here. And so the mass is rho times v, which came out to be 4.22 kilograms. Some of you got 39, and I was going, why do they think this mass is 39? And I figured it out. You squared this instead of cubed it, and then you get 39. So I was like, oh, that's the only thing they screwed up. So, well, for some, that was the only thing you screwed up. Others, there was a long litany of things, so that wasn't the only thing, but that's okay. You're in there pitching. All right, so that's the mass of it, and then I of the thing, which I put in. Now, this is not the kinetic energy. That was another thing that caused problems with certain people, was in the kinetic energy question, I said I equals, that was just to be helpful, equals 2/5 mr squared. Okay? So that would that came out to be like 0.0196 kilogram meters squared. Okay, so there, everything's set up that we need to be able to do this problem. Oh, except for one last thing. V equals 12.7 meters per second. Now that's the rolling, that's the center of mass. So omega, V center of mass equals Vt, which equals R omega. So omega was equal to 12.7 divided by 0.108. And that came out to be about 118 radians per second, right around there. All right, so that was A. B was this guy. You got something rolling. It's going 2V up here, V right here, and 0 right here. So this was just equal to 12.7 times 2, which was 25.4 meters per second. Some of you doubled this. Now, does this guy ever change? Once he starts running, no, he doesn't change. V changes. V's change. This is for translational motion. All right, and then C. Here's the casualty count was high. All right, on C and D. All right. Now, to find the total kinetic energy. This guy hasn't gone away yet. He's still there. That's his translational kinetic energy. Plus, you have his rolling kinetic energy. Okay? So you have this and this and this and this. And this came out to be right around 464 or 470 joules. Okay? Some of you got 1,200. I was like, why did they get 1,200? Aha! I know what they did. They had the mass again was 39. Another common mistake was you got like 136. Well, that was just because you just computed this guy. You left him out. Some of you actually computed this and computed half of this, and it was such a small number you kind of threw it out because you forgot to put in the radians per second squared, or you just multiplied it by radians. That was just, there's so many little algebraic things you got to put in there. It's just fraught with peril under test conditions. It's difficult. Okay, I got to kind of keep that in mind too. That's why I'm a firm believer in partial credit and stuff like that. So this is C, and then D. I got several comments from students saying, "Well, I need an incline." Oh no, you don't want to go down that road. You don't want an incline. You don't want to do that. Don't do that. Just use energy. In other words, once it stops, once it goes a certain height, and it stops, then all its kinetic energy has been transferred to what? Potential. So you take this KE equals mgh. And so whatever answer you had there, 464 we'll go with, divided by mg gives you h. Gives you how high it'd roll up the thing. It seems real easy now, doesn't it? Seems like, oh yeah, duh. Okay. That's why I like to go over them. You can just pass them back and go, well, but the object is to learn something. Good. Okay, besides the fact that you don't like physics. I don't want you just to learn that. All right, now. Okay, then the next one. This is the one I just made. Now, I just made these were 10 points each, okay? Vice 20 each. I don't know why I had them originally as 20. But by the time I was grading years, everything was fine anyway. So some students were going, well, then I got punished. No, you didn't, because everything's arbitrary anyway. Everything, you know. All right, so. Okay. All right. So on 6A, on part A, you had the tension was equal to 1,300 newtons. So therefore, T equals mg. So M equals T over G, which also equals rho V, which T over G equals rho times x cubed, because we're just looking for a cube here. All right? So if you get this kind of, I kind of like this one. If you put rho times G, it looks like some kind of, I don't know, neat tattoo or something. Third equals x. Some of you got to this far. There's quite a few who got to this far, and then were stumped by your calculator on how to get the cubed root. And you kind of hit the second root twice, so you got a little bit bigger number. But it came out to be about 0.35, 0.34 meters, right around there. Okay, now, then the second part really had nothing to do with this part. All right? Oh, I know what a big mistake was on this one. People misread the problem, and they thought that the area of the nylon cord was one of the surface areas of the cylinder, of the cube, of the crystal cube. No. And so they're going, oh, well, then rho times A times H or times X equals mg. No, can't do that. And they wound up with, like, the thing was like 75 meters long or something. I was like, that's a big chunk of crystal. But, or something, I don't know. It kind of came out funny. But anyway, so that's that one. Then the other one was just good old Young's modulus, which is F equals Y times delta L over L naught times A. F over A equals that. Okay? Or the pressure equals that. And so you're just looking for delta L. So that came out to our classic Flow-ya problem. Equals delta L. All right? And the biggest problem that people have is putting scientific notation, putting those big screwy numbers in their calculator. So if you got that far, I gave you at least 3 points for if you showed that. I was like, okay, at least, and you put the right numbers in there, and you showed that this was 1,300, this was 1.5, this was 5.0, I think, times 10 to the 9th for nylon, and A was 1.7 times 10 to the negative 4th meters squared. Yep. All right, and then the last problem, polar bear on ice. Polar bear on ice. Some of you guys did a pretty good job on this. You thought through it. Now remember, if I want to submerge 5.2 cubic meters of something in water, I'm going to have to, in seawater especially, seawater is 10 to the 25th, so that's why we say it's more buoyant, because it's more dense, so things float in it. Any of you been to the Great Salt Lake? Floated in Dead Sea? I've been to the Dead Sea. It's kind of weird. It's real oily when you get in there and you just float around. It's strange. But anyway, you go, people have been fighting over this for 6,000 years? But anyway, all right, so so the max buoyant force, to put that thing completely under would be 1025 times 5.2 times G. Well, G is going to cancel out, so we could just go with the max mass, buoyant mass, or whatever. Mass would be 1025 times 5.2. That's the max. So 1025 times 5.2 equals 917 times 5.2. That's the ice plus the mass of the bear. Some of you gave me the mass, some of you gave me the newtons. Either one would have been fine. So you just subtract. It really came out to be this simple. 1025 minus 917 times 5.2 equals the mass of the bear. There. Okay. And that came out to be about 560, something like that, kilograms. All right. So it was a few heavy rolls, but it wasn't a total disaster. So I've looked at the Your overall grades are still okay. Nobody's okay. Now then, let's talk a little bit. Let's finish up chapter 9. Let's talk about your homework 14, number 14, because we've done problems from 13. So let's make it worth your while that you came in today. Oh yes, thank you. Let me put this here, and these guys go here. I got quite a few of these passed back this afternoon, too. There we go. All right, now, we're going to talk about fluids that are moving, okay? When fluids are moving, strange things happen, all right? And what we're going to do is do your homework, or get you started, or basically do it, because it's due like after Thanksgiving break here. You don't want to be working on it the Friday after Thanksgiving or something. There's probably a football game to watch. All right. Now, okay, so when things start moving, here's the big deal. Here's the deal. Bernoulli's principle, all right? Bernoulli's equation, Bernoulli's principle. Here's the thing. When things are flowing, and we've got to meet these 4 conditions. All right, I'm just going to, I hate to read out of the textbook, but I didn't want to write it down then read it, so I'll just, okay, 4 things have to happen. We have to have an ideal fluid. That means it's incompressible. That means it's water, basically, type thing, okay? And we are not going to be looking at eddies or anything. So condition 1, the steady flow rate means that all particles of the fluid will treat air just like the fluid, have the same velocity as they pass through a given point, okay? All right, now this is not true in a pipe. In a real pipe, you've got water flowing through and it flows fastest in the middle, because as it gets to the edge, there's frictional forces that are slowing it down, so those are slowing down the other particles that are a little bit closer, and then pretty soon it gets ignored, and they're going pretty fast in the middle of the pipe. All right, now, the first thing we're going to look at is the garden hose thing. You know, when you squirt your little brother or sister with a garden hose, you've got this. It's the continuity. Oh, and condition 2, let me finish the conditions. Condition 2 is irrotational flow. It means that a fluid element, a small volume of the fluid, has no net angular velocity. In other words, it's not causing whirlpools or eddies or anything like that. Fluid mechanics, the whole study of fluid dynamics and fluid mechanics, is a whole branch of engineering. There's hydro engineers. In fact, my, I guess, new son-in-law is a hydro engineer who started out that way. Okay, and where they just study the flow of how fluids flow and things like that. It's got to be non-viscous. All you taking chemistry, you know what viscosity is, right? Viscous fluids have a lot of friction in them, so they don't flow very easily. It's like the difference between honey and water. Honey has high viscosity. Water has low viscosity. Which is more dense? Blood, or you bio people, blood or water? Or is it about the same?
Well, blood has a high water content, so, I mean, it'd be technically water less.
Technically, very, very little.
Because, I mean, when you centrifuge it, you know, the cells go to the bottom and you have liquid water, plasma.
Right. Yeah, I used to do that. That's how I got my beer money in college, give them plasma. Still have my track marks, too. Twice a week. It's a great way to get rid of a hangover, because they'd take your blood and then they'd put that saline solution in your well. It was like, oh, cool. All right. So, I don't recommend it, though. When my mother found out, she about died. She had a conniption. But hey, it was $6 the first time you went, $8 the second. I think it's a little bit. It's quite a bit more now.
It's like $50. They get drawings and stuff.
Wow.
It blows your veins.
Right. Yeah, they have a hard time getting the blood sometimes. And I got scarred to death. All right, now. Anyway, so and you actually have a problem. So we'll look at that problem that you have. basically what we're looking at is the continuity, equation of continuity, which basically says this. As, you know, as something is flowing through a pipe like this, and here's the mass of it right here. It's going like this. This is A1, V1. When it hits here, A1, V1 is going to equal A2, V2. So here's really what's going on. If A1 is big, then V1's small. So what do we have over here? If A2 is small, what's our V2? Big. It's bigger. Now, you have a problem that deals with this. Excuse me. It is problem 63, all right, that I've given you. And it says, oh no, problem 63 is a different problem. That's a hard problem. We'll look at that one later. We'll look at that last. But I did give you, I gave you problem 61, blood flow. That's it. Yeah, problem 61. It says the blood flow speed through an aorta with a radius of 0.1 centimeter. So if R equals 1 centimeter. Okay, first thing we got to do though, since we're dealing with the pressure in kilograms per meters cubed, I know you chemistry people hate this, but we've got to change this guy to meters. So R equals 1.00 times 10 to the negative 2 meters. There we go. And it's going 0.265 V1 equals 0.265 meters per second. They want to know what its velocity is. If the hardening of the arteries causes the aorta to constrict to a radius of 0.8 centimeters, so now R2 is equal to 0.8 times 10 to the negative 2 meters. Okay? They want to know what the difference is between V2 minus V1. Be careful. That's what they're asking. Because when I did this problem, I was like, oh, this is easy. V2 equals, because I just set it up. I went, okay, the pi's will cancel. Because basically you get pi times R1 squared times V1 equals pi times R2 squared times V2. And so V2 equals pi R1 squared V1 over pi R2 squared. So the pi's cancel. And I was all fat, dumb, and happy. I was like, oh, that's great. I got it. No, I didn't. I got it wrong. Because they said, what's the difference? So be careful with that. So go ahead and get your V2 and then subtract the V1, and you'll get the difference in the speed. Okay? And when that closes up, see when your veins harden, now this is very simplistic. This is not by any stretch a medical thing, but when your veins harden, that means the blood has to pump harder. Your heart has to work harder. It causes more pressure on it because it's going faster out the other end, out those smaller ends, so there's more pressure building up behind it. Okay. So that's the continuity equation. Now, you've got this other funny problem that I want to talk about real quick that has, let me go ahead and go to the Bernoulli thing, and then we'll talk about the two funny problems that you've got. And then we'll pretty much be done for the evening. It'll be a short one right before Thanksgiving break here. All right. So here we go. So we've got... here we go. Based on the continuity equation and a few other things. All right. In other words, pressure 1, P1 plus 1/2 alpha V1 squared plus 1/2 rho GH1. These are all pressures that we're given. That equals some constant. Okay? Equals some kind. This is with moving air and everything else. All right, so fast moving air has lower pressure than slow moving air, but Mother Nature is always trying to get that stuff to balance. The forces are conserved, all right? And this comes from, this is the Daniel Bernoulli work that he did, where he said the net work done on fluids is equal to its change in kinetic energy plus its change in potential energy. Okay? So that's where we get this stuff. Now, it looks scary, but I'm just putting it up here. 1/2 V2 squared plus, this isn't 1/2 GH, it's just rho GH. It's not 1/2 that. I lost my mind there. 2, height 2. Okay? Now, mainly what we're looking for is, what's the difference in pressure between two things? Okay? What's the difference in pressure? So that's what we're always looking for. We're looking for the difference in pressure. What's delta P, which is basically P1 minus P2. We're looking for that, equals, if we rearrange these equations, we get this up here. 1/2 rho of V2 squared minus V1 squared plus rho G of H2 minus H1. Those equations will hold us in good stead. Now, so let's go straight to one of your problems that you have here. And your problem looks like this. So we've done the aorta problem. That was problem 61. Now you've got this funny looking problem that looks really hard, problem 36. And basically what 36 says is, I've got this vat of water, and we're going to keep it at a constant volume. So we got water pouring in here to keep it at a constant height. Also a constant volume. I wasn't wrong about that either. But outside of this thing, I've got a little pipe right here. Okay? And it's shooting water up like this. They want to know how high that water goes. I'll tell you what. You can just look at the picture. Yes, Brad?
When you were writing it, you said 1/2 alpha V squared.
I meant rho. Yeah, I meant rho. Did I say alpha? I meant rho for the density. Yeah, yeah. Yes?
When you have a delta something, like doesn't be the P2
It doesn't matter because we're taking the absolute value of it. That's right. You're right. That's usually the case, okay? But I'm fudging here so that it'll all work out nicely. Okay, so you know what you can do with this problem? You know what you can do with this problem? You know what you can do with this problem? You can do this. You can go, what's the air pressure right here? And what's the air pressure right here? They're the same thing. They're the same thing. So the difference in air pressure is the same. So this is 0. All right? So the difference in my two heights is going to be what? In other words, first of all, how fast are these fluids flowing at this stage and at this stage? This is where it reaches its terminal velocity. I mean, it's done flowing. It's got all its velocities down here. Then it's going up here, and then it stops. Because if it still had a velocity up here, it'd still be going, right? So the two velocities are what? 0. Well, right. Because right here, what's the velocity of this fluid? 0. Right up here, it's 0. But what's the height? So this whole thing has to equal 0. So you've got this height minus this height has to be the same thing. So guess what? They tell you what this height is. So guess what this is? Half price store. It's the same thing, right? Because my change in pressure at the very top there is 0. So that's a nice little thing to know. All right? Now then, there was kind of a cool problem in the old book that I kind of liked that I'll talk about real quick on when we got air flowing. Okay? This was a problem where the two heights are the same. So when you go to your problem 36 and it says it is kept at a certain height, guess what you're going to do? You're going to just type in that height for your answer. It'll be good. Because it works out like this. All right. So anyway, so it had a problem like this. It had the area, basically it showed if you got the wind blowing this way, by the way the prairie dog home was constructed, like this. You had these little prairie dogs living here, down in their little burrow. Here's a little prairie dog burrow. All right, you had the wind was blowing like 8.5 meters per second over here, but because of the way the thing was constructed right here, it was actually going 1.5 meters per second over here. All right, so we had to find a change in pressure. So if there's a pressure difference, and there is, because see this one is going faster than this one, and they're at the same height, so you can cross out these two. And so P2, the change in pressure, is equal to V2 squared minus V1 squared. By the way, rho of air is 1.29 kilograms per meters cubed, all right, which is what we're going to use. But anyway, so this causes a change in pressure. Where's the pressure greater? Over this hole or over this hole? Over hole A or over hole B? Which way is the pressure greater? B. So you got more air pressure pushing down here, so that's how they get their ventilation. Okay, so that's how burrowing animals, they just know how to do this, so that's how they get their ventilation. Okay, so if you want to ruin their day, you make it like that on both sides. Sleep tight. Okay, you know, and people get all upset when I say that. Go, oh, prairie dogs. Hey, if you're a Kansas wheat farmer or cattle rancher, you don't need prairie dogs because you're going to lose cattle and stuff like that. So anyway, but I don't know if that'd be humane or not, but anyway. All right, so that gets us to your penny problem. I love this problem. This is a cool problem because we don't want to ever forget. And I actually tried this. Being a physics instructor, I went, well, I could do this. Tried to blow a penny up in the air, and I couldn't get it to work. I can bounce a quarter into a cup, though. I'm very good at that. All right, but I could not get this penny to blow in the air. At least I used to be good at getting a quarter to bounce into a cup of Coke or whatever. All right. Or, yeah. Yeah. What's that? Oh, yeah. But it was like a hangover. Well, I'm sorry. I don't need to go into that. Okay. All right. Now, the penny. Yeah. Okay. So what we have, don't forget this now. Don't forget that pressure equals F over A. So what we're looking for in this, where this professor is blowing over this penny, all right? He's blowing over this penny with a certain velocity, all right? Now before it's got a different pressure, and the air pressure is different underneath here, all right? And so we're looking for that change in pressure that will cause this penny to flip up in the air. So we're looking for this velocity 2 right here, because velocity 1 equals 0 underneath the penny here. Velocity 1 equals 0. And V2 is what we're after. H1 equals H2. So those two, this goes away. So what we're looking for is a change in pressure, but you got to keep in mind that the change in pressure is always equal to F over A. So what's the force that this thing is pushing down, this penny? Good old mg. Okay? Good old mg. Now, they give you the penny in grams. Now, I know you chemistry people like to work in CGS, where you use centimeters and grams and all that stuff. In physics, we use meters and kilograms, SI units. Okay? Otherwise, you get into, see, we use joules, which is, what is joules? Newton meters okay? And you guys have dynes, which is the Newton's thing, which is grams per centimeters per second squared. So you got dynes. So here's my joke. Make sure you get this on film. All right. No, I'm kidding. Dr. Steiner's going to kill me. What is this guy? Yeah, well, he's a centimeter. He's a centimeter. What's this guy? Oh, that's pretty good too. No, he's an erg. He's a dyne centimeter. Oh. Because dynes are newtons, Newton meter, they call them ergs. They actually call too much explaining. I had to explain that one too much. All right, let's go back to blowing the penny. Since we blew that joke, all right, let's go back to blowing the penny. Let's go back to the penny problem. All right, so good old MG's what's down here, and the area is the area of the penny, and they give you the diameter, so cut that in half. Now remember, when they give you centimeters, you have to be careful because when you square that, that's meters to the -4th when you square it. All right, so this just becomes, so basically your change in pressure then is just your change in your two velocities. So you get 1/2 rho v2 squared, because v1 squared is equal to 0, equals your, because this is your change in pressure, will equal mg over pi r squared. And you just take it from there and solve for v on that problem.
And we put the row of air in.
Yeah. Row of air is 1.29. .29 kilograms meters cubed. Okay? All right. So that's that problem. So there we did about 3 of them. Let's look at one more. Let's look at, this is more Pascal's principle, but Pascal's principle evolves into this. Let's just learn how to read the problems, because on your last test, which will be given when the finals are given, okay, we'll cover this last little section of chapter 9, so you'll have a couple piston problems maybe. We might even blow a penny, or we'll change it to a dime or something like that. And you can get out of the final if you can actually make that work. But anyway, what we're going to do is that last half, and then I've got to figure out, this book has the whole wave and simple harmonic motion in chapter 13. I think we need to look at that for a second. But we also have to do temperature. We're not going to get to thermo. And so when we come back from Thanksgiving, we only have 3 class periods left. 3. I can't do 4 chapters in 3 classes. I could and say I covered it. You know, I could just flash through the slides. I don't know if you'd learn anything, but anyway, that looks like Oklahoma. This is Delta. Okay, now so I'm still trying to figure out what the last, pretty much chapter 10, because I think your next lab is going to be temperature stuff. So we'll definitely look at temperature. That's important. Well, it's all important, but got to figure it out. So anyway, let's look and see how you do these problems, because you'll have an output. Now remember, Pascal's principle is this: the force of the input over the area of the input, which is a pressure. Again, P1 equals P2 in this case, so the change in P is equal to 0 because it's distributed equally throughout, is equal to the FO over AO. All right, so here's what they do to you, so you've got to be careful. They said the output piston, this is problem 38, the output piston of a hydraulic press has a cross-sectional area of 0.25 meters squared. So the output equals 0.25 meters squared. And then it says it says how much pressure on the input piston is required for the press to generate a force of 1.5. We want FO to equal 1.5 times 10 to the 6th newtons. I think it's 1.5 times 10 to the 6th newtons. Yes. All right. How much pressure do we need to put on that piston so they can lift 1.5 million tennis balls? Basically, that's what we're saying. All right. So here we go. Well, it says how much pressure? Well, we want the incoming pressure is equal to Fi over AI, which equals, oh, look at this. 1.5, or, yeah, times 10 to the 6 newtons divided by 0.25 meters squared. Well, there it is. That's it. Just wanted you to get used to seeing how they're, and then, of course, they ask, hey, if AI is equal to, now here's where you got to be careful. If AI is equal to it has a diameter, AI has a diameter of 5 centimeters. Whoops, it's got a radius of 2.5 times 10 to the negative 2 meters. So you got to put that in. So AI would be pi times 2.5 times 10 to the negative 2 meters squared. And they want you to find Fi. Well, that should be pretty simple. Because if you're given this guy, these two guys, so you've already know what so I just use my answer from this, multiply it by AI, boom, you're done. Right? That's probably kind of quick. Steve's going, wait a minute. What'd you do? I'm saying if you've already computed this, then if you're trying to find this, all you got to do is just multiply both sides by AI and you've got it. You're on your way. Okay? There, that's like the last 4 or 5 problems of those 8. Well, I think we did the first 3. All right. We are done. Have a safe holiday. Please have a safe holiday. Come back in one piece. All right. Stay away from plasma donor centers.